Hi again. Today I will continue with the ideals. Remember, at the end of last, at the end of last lecture, we defined what's prime ideal. What's prime ideal? Let's recall. In a commutative ring R, an ideal is called prime. An ideal P is called prime. Let's choose some here. An ideal P in R is called prime if whenever x, y is in P, then either x is in P or y is in P. And so let's, as a proposition, we stated that let R be a commutative ring with 1, and P is a proper ideal. Then characterization of prime ideals is that if R is a prime number, a prime ideal, if and only if the quotient is a R over P is an integral domain. And for the proof, let's remember what did we do for the proof. So we started this way. So suppose that P is a prime ideal. So since R is commutative ring with 1, then R over P is a commutative ring with 1, and the 0 of this ideal is R over P, P over P, which is the left quotient of 0, if you like. And suppose let's take two elements x and y from this P. Two left cosets from R over P. Suppose that their product is 0. We need to show that one of them is 0. One of them is 0 in this quotient ring. So that will imply that R over P has no 0 divisor, so that it's an integral domain. So that P is x plus P times y plus P, but by definition this is x times y plus P. So that means that x times y is in P. Since P is prime, either x is in P or y is in P. So that means either x plus P is equal to P or y plus P is equal to P. And remember, P is equal to 0. So therefore, R over P has no 0 divisors. Hence it's an integral domain. Now, suppose conversely that R over P is an integral domain. So conversely, suppose R over P is an integral domain. And let's show that P is a prime ideal. P is prime. P is prime. In order to show that P is a prime ideal, we need to show that whenever x times y is in P, x is in P or y is in P. Okay, so let x, y be in R with x times y is in P, so that if you look at this, x times y is in P, so that means x times y plus P is equal to P, or it is equal to P. That's equal to 0 of this quotient. Let's do it like that. So that, but x times, so that x plus p times y plus p, which is the x, that's equal to x times y plus p, that's equal to p, which is 0. So since R over P has no zero divisors, since it's an integral domain, it has no zero divisors. So either x plus p is equal to 0 or y plus p is equal to 0. 0 is in this quotient ring, this left coset p. So that means, i.e., either x is in P or y is in P. So whenever x times y is in P, we show that, let's use this thing. So whenever x times y is in P, we show that either x is in P or y is in P. So that means, therefore, P is a prime ideal. As it should be. Okay, now let's, as a corollary of the statement, so remember in the integers, all we showed that all maximal ideals. Okay, before this, okay, I didn't prove this. So here's an example. So let P is prime. So that P, so that we have a maximal ideal is maximal. So, or maybe I should start this way. Maybe I should start like this. So let before this, so let M be a maximal ideal in Z, so that there is a prime P such that M is equal to P times Z, as we showed in the previous lecture. So let's say, suppose that x times y is in P times PZ. This is small p, PZ, so that x times y is equal to P times n for some n. So since P is prime, so therefore P divides x times y. Since P is prime, it divides either the P is, this is small p, not the capital P. So since P is prime, P prime, this implies that either P divides x or P divides y. So that means P is equal to x. Okay. If P divides x, so if P divides x, then x is equal to P times L, so that x is in PZ, which is M. And if P divides y, similarly, we write y is P times L prime, so that y is in M. So therefore, M is prime ideal. So the maximal ideals in Z are, so therefore maximal ideals in Z are prime. But we showed this in in Z, but this is true for every ring. For every ring, it is true. So the corollary of this above proposition that let R be a ring, commutative ring with one, and let I different than R be an ideal. Then if I is maximal, then it is prime. So here's a proof. Proof is the combination of the two statements we proved about maximal ideals and prime ideals. So since I is maximal, we show that R over I is a field, and every field is an integral domain, so that R over I is an integral domain. And if the quotient is an integral domain, as we proved above, then I is, by the above proposition, I is a prime ideal. So that the maximal ideals are prime. And the prime ideals are not maximal. Note, prime ideals need not be maximal. Example, if you look at zero ideal in Z is zero ideal in Z is prime in Z, but not maximal. But it is not maximal. So prime ideals need not be maximal. Okay, next. The question is, let's try to answer this question. The following question. So given the ring R, can we embed R into a field? Can we embed R into a field? Namely, does there exist monomorphism, group ring monomorphism such that monomorphism phi from R to a field K, where K is a field? That's the question. And for integers, this is certainly true. For integers, for example, you look at R to be the integer Z, then R is inside, can be, there's a monomorphism from Z into Q or R, or you can, or the complex numbers, and you just define phi of n to be n, for example, so that we can embed this Z inside the field. But also, yeah, let's write it. Also, we can embed this integers Z into complex numbers. Just take n to be n goes to n plus 0 times I, for example. So these are ring homomorphisms, ring monomorphisms. And let's consider this. Consider rational numbers. Consider Z as a subring of Q. So we can write every element of Q is of the form R over S, where R and S are integers. Yes, as we know this. Okay. Now, here's a lemma, but so lemma is this. So this Q is, I should write Q like this. So suppose, so here's a little lemma. Let F be a field. Field with this property containing Z like this. So remember, rational numbers contain Z, but suppose that there is a field in between them, then F is equal to Q. And here's the proof. So we need to show that every element of every rational number is contained in F. So let R, which is A over B, be a rational number, so that A and B are integers and B is not 0. So that A is in F and B is in F. Since B is not 0 in the field, then B inverse, namely 1 over B, must be inside F. The reason is F is a field here. F is a field. So therefore, R, which is A over B, A times 1 over B, is inside the field of F. So that means rational numbers are inside F, or rational numbers is equal to F. So that means, in some sense, field here, I should write field, yeah, field with. Okay, therefore, so Q is the smallest, in some sense, smallest field, in some sense, containing C. So this is, we can do this for any integral domain. Well, integral domain, but remember, integral domain is a commutative ring with 1, which has no zero divisors, but the integral domain need not have 1 in this in the following, but I will just express that. Part. Here's a definition. So let me divide this into 2 pieces first. Okay. Okay, here's the definition. A field of fractions of an integral domain R domain R is a field. Therefore, let's denote like that, FR with a monomorphism monomorphism phi from R into f of R such that if K is any field, and theta from R to K is a monomorphism, then there is a unique homomorphism, which is necessarily a monomorphism, necessarily one-to-one. Homomorphism f of R into K, such that f times little f composed with phi is equal to theta, namely, i.e., this following diagram comes. The following diagram commutes. So phi is commutes. So the diagram is like this. So we have a monomorphism from phi from R to f of R. So it's an embedding. An embedding is a monomorphism. And if we have another field, K, so this is phi is fixed. And if we have a monomorphism like this, theta from R to K, then there is a unique homomorphism like this, such that this diagram commutes. So this diagram commutes means f. So when you go by phi first, and then by f from R, and also that should be equal to theta. Okay. An example is you can, as an exercise, so Q is a field of fractions. Of Z, and the embedding is this phi is from Z into rational numbers is phi of n is equal to n, just n over 1, n or n over 1. So just like these rational numbers constructed from integers, then we can, from an integral domain, we can construct a field of fractions. So it is a proposition. So if there is an integral domain, R, which is not 0, has more than one element, is an integral domain. Then R has a field of fractions. Or a field of fractions, which is a field of fractions f of fr, and which is unique up to isomorphism. Namely, f of r is unique. So here's a proof. So remember the oops, what did I stated? So let me say it like this: if R is an integral domain, and if R has a field of fractions, then F is unique. FR is unique up to isomorphism. So I will prove the existence later. First, uniqueness. Proof. Suppose that we have two field of fractions. So let these are two field of fractions. With phi r to f of r and phi prime f of r to f of r prime. These are injections, monomorphisms. So we will show that fr and fr primes, fr prime are isomorphic. So let's consider this fr into fr, this phi, and we have another field fr prime, and then a monomorphism like this. So since f of r is a so there is an f like this, a homomorphism such that phi f is equal to phi prime, since fr is a field of fractions, and conversely, also phi prime, fr prime is a field of fractions, so that phi prime is 1 to 1. So since fr is a field, since fr is a field, there is a homomorphism like that, and we have a monomorphism like that from R to fr, so that we have a map, we have a monomorphism this way, G, so that G of phi prime is equal to phi. So therefore, phi is equal to G times phi prime. But instead of phi prime, let's write G f phi. Also, phi prime is f phi, which is f g phi prime. So now from R to fr, we have the homomorphism phi, and also we have the phi like that, and we have two maps, two injections. One is the identity map, making this diagram commutative, and also f times g. So g times f. G times f. So this implies, since this homomorphism must be unique from fr to fr, so g of f is identity of f of r. And similarly, fr prime is a field of fractions. F composed with G from also this, using this inequality. This is the identity of f of r prime, so that this implies that f is an isomorphism. From fr into fr prime. So that field of fractions, if it exists, it is unique. And here's an easy exercise for you. So every field is an integral domain. If R is already field, then it has a field of fractions, and f of r is equal to r. And here's a theorem. This is the existence of field of fractions. Existence of field of fractions. Oh, by the way, this is also called quotient field. Quotient field, or field of quotients. Yeah. Okay, here's a proof. Here's the proof. So let R star denote R minus 0. So consider integers, and X is X R cross R star. So define a relation on X as follows. This is the Cartesian product. This is Cartesian product. Define AB and CD in X are equivalent if and only if AD is equal to BC. I will leave this to you as an exercise. Show that this is an equivalence relation. Equivalence relation on R. On X, sorry, not R. On X, it's an equivalence relation. And let's denote the equivalence classes. Classes of equivalence class of an element AB by A over B. So let's denote equivalence class like that. Oops. So that and let FR denote these equivalence classes. So that X over this equivalence class. So that that is A over B such that A is in R, B is in R star. So B is not 0. B is not 0. Let's define, so I define two operations on this FR, addition and multiplication. Let's define, just like addition and multiplication as in rational numbers, define A over B plus C over D is equal to AD plus BC over B times D. And AB plus times, sorry, CD is equal to AC over BD. And so you need to check that this is well defined. These are defined, depends on representatives. You check that these are well defined. These operations are well defined. And this f of R is a field with these operations. So in order to show that it's well defined, if A over B is equal to A prime over B prime, and the C over D is equal to C prime over D prime, you need to show that A over B plus C over D is equal to A prime over B prime plus C prime over D prime, so that it is independent of the representatives, and also A over B times C over D should be A prime over B prime times C prime over D prime. You need to show these equalities. And also with these operations, f of R is a field. I will leave this to you. And the zero element of this f of R is, zero element of f of R is 0 over B for any B. And if we take A over B, it is additive inverses minus A over B. And the 1 is 1 over 1, or A over B for any B, or any B not 0. Okay, and if AB is not 0, so that means A is not 0, so that BA is in FR, and AB times BA is 1, so that the inverse of AB is B over A. Okay, now define phi from R to FR. Like this, phi of R is R over 1, or that's equal to R over A times A for any A is not 0. So these are the same. And with these operations, phi is a homomorphism. So let's check that phi is a homomorphism. Phi of R plus S is R plus S over 1, which is R over 1 plus S over 1, which is phi R plus phi S. And R times S, this is the multiplication in R. It is RS over 1, and that is R over 1 times S over 1, which is phi of R times phi of S. So that it's a homomorphism. Let's look at the kernel of phi, that is R in R, such that phi of R is 0, and that means R in R such that R over 1 is 0, so that R must be 0 only. So therefore, kernel of phi consists of only 0, so that means phi is a monomorphism. Phi is 1 to 1. Okay, good. So we have a field. So we have a field. We have a field FR and a monomorphism from R into FR. Now, suppose that F is another field. Suppose that K is a field now. K is any field, a field. And theta from R to K be a monomorphism. So that we have this diagram, R to FR. This is phi, this is theta, this is the field K. So we need to show that there is an element F like that, so that this diagram commutative. There's a homomorphism like that. So let's define F from F of R into K, like this. F of A over B as, so A is in R, B is in R, so that theta A is defined, theta B is defined, theta B inverse. So theta B is not 0, since theta is a monomorphism. Since B is not 0, theta B is not 0. Okay, then this is well defined. So F is well defined. We need to show. Why? Because if A over B is equal to C over D, this means that AD is equal to BC, so that since theta is a homomorphism, theta A times theta D is equal to theta B times theta C, not phi, theta C. And if you, so that if you multiply by the inverse of these elements, theta, not C, B, these are non-zero elements. These are non-zero elements, so that theta A times theta B inverse is equal to theta C times theta D inverse. Oops, D inverse, so that this is f of A over B is equal to f of C over D. Okay, so that there are three things to check. F is homomorphism, and it's also one-to-one. It's also one-to-one, and so I will skip that part, and this for any A in R, A of R, so then the phi of A is A over 1, and the f of phi of A is the f of A over 1. This is theta A over theta, this is A, theta A over theta 1 inverse. Since this is 1, so that is theta A. So therefore, f composed with phi is equal to theta. So this is satisfied. There is one more thing that I will skip. This f is unique. One thing that this f is unique. I will skip that, so that every integral domain has a field of fractions. I hope time is up now, so I have to quit here.